Okay, so yesterday we were talking about Newton's second law and how it applies to systems. Okay, so a system is anything that has basically more than one mass that's moving together. We looked at pulleys, okay, and we looked at just pulling two masses along that are attached by a string, and then we looked at this one, which is two pulleys. Does that change anything? It doesn't. You can put as many pulleys as you want into a system. It doesn't change anything except the direction the force acts. Okay? It's still the same amount of mass that has to be accelerated by the same amount of force. All right? So what we're looking at here is first identifying the forces that are acting in this system. So the first thing they tell us is that this table is one of these magical frictionless surfaces. Okay? That doesn't, so we don't have to worry about any drag anywhere. All right? We do know that these pails are 8 and 6 kilograms respectively. Okay? And since they're hanging off of a pulley, what's acting on them? Gravity. All right, so we've got gravity acting here. That'll be 58.86 newtons. And then here, 78.48. Is that right? Yeah. All right, we calculate those by just going mass times 9.81. All right, those are the forces in this system. There's no friction. Okay, that's it. These two forces are actually acting against each other. Yeah, one's pulling, yeah, I mean, they're both pulling down. Gravity only acts one way. But because they're being offset by these pulleys, they're actually working against each other. All right, so we've got the 20 kilogram tire. We've got 6 kilograms on this side, 8 kilograms on this side. What's going to happen in this system when I release it? Which way will the tire move? Yeah, to the left, towards the 8 kilogram mass, because there's more force pulling the system, okay, that's all of the mass, that way. Okay, so what I'm going to do now that I've got the forces identified is I'm going to simplify this. It asks me for the magnitude of the acceleration of the system. Notice it only asks for magnitude because I can't give a direction. All the parts of the system are going to accelerate, but one of them's accelerating down, one's to the left, and one's up. Okay, so I can't give a direction for the system because all its parts are going different ways. Okay? All right, so I'm going to simplify this system to this. 34 kilograms worth of mass are going to be accelerated by the net force that is the result of the two pails being pulled by gravity. All right, that means that the system's being pulled this way by 58.86 newtons and this way by 78.48 newtons. Everybody with me so far? Okay, what can I calculate now? F net. Using m times a or sum of all forces? Sum of all forces. Okay, so F net is simply going to be 78.48 plus negative 58.86, or just subtract it, and that's going to be 19.62 newtons is my net force. All right, so that 19.62 newtons has to accelerate the entire system, all 34 kilograms of it. Everyone all right with that idea? Okay, how do I calculate that acceleration? Right, F net equals m times a. I now know what the F net is. It's 19.62 newtons. I know the mass of the system is 19.62. I just have to find the acceleration of the system, which is what the question is asking for. So I'm going to divide both sides by mass. So that's going to be 19.62 newtons divided by 34 kilograms. What did that come out to?
0.577.
That sounds about right. 0.57, and we have two significant digits here, so 0.58. 0.58 meters per second squared. There's the acceleration of the system. Okay, again, did we do anything different? Every single time. Sum of all forces and m times a. Okay, yes, it's becoming increasingly complex to get there. Okay, but in the end, that's what it always breaks down to. Okay. Questions on that one? Okay, now there's different ways to give you a question like this and word it to trick you. Right? We talked about that yesterday, that I would totally do that. Okay, by asking not for the acceleration of the system, but for asking for the acceleration of the tire. Right? And what did we say the most common mistake would be if I only asked for the acceleration of the tire? What would people do? Okay, well they might try and include gravity here, but that wouldn't be the most common mistake. Right, instead of using the mass of the system and recognizing that the whole system has to be accelerated by the net force, they would just do the tire. Because the question said, what's the tire? Okay, and people forget there's more to the system than just the tire. More than just the tire is being accelerated by the net force. Okay? All right, so now, same example, but now we want to calculate the acceleration of the tire. Okay? If the mass of pail B is increased to 12 kilograms. So let's just bring that picture over. Okay, so we'll bring that over. Okay, so the pail B is increased to 12 kilograms instead of 8. Okay, pail C is still 6.0 kilograms. The tire is still 20 kilograms, but we're increasing pail B to 12 kilograms. Okay, and then for number 2, it's saying same situation, but now we go back to pail B being 8 kilograms, and we're replacing the truck tire with a car tire that is lighter, only 15 kilograms. Okay? All right, so give those two a try. Let's see how we do on those. Keeping in mind, I already told you what the trick in these two questions is. Right? They just talk about the tire. So for this first situation, for question number 1, we've got a 12 kilogram mass on the left, 6 kilogram mass on the right, 20 kilogram tire on top, right? And we are looking for the acceleration of the tire, which is the same as the acceleration of the system. That's what I have to find, is the acceleration of the system. The only thing that's going to change here is now I can also give, in addition to a magnitude, the direction, because it's asking about a specific part. I can say the tire is going to move to the left. Okay, so it's still going to be same idea here. This is going to be 117.72. Yeah, newtons. Okay, this is still going to be 58.86 newtons, right? As our two driving forces, there's no friction here, right? So we go back to simplifying the system. Right now it's not going to be 34 kilograms, now it's going to be 38 kilograms worth of mass. 58.86 going that way, 117.72 going this way, right? We can calculate our net force in the same way we did on the last one. Sum of all forces. It's going to be 58.86 newtons, because this mass is twice that one, so the force of gravity would be twice the other. Everyone okay with that? Okay, I'm shortcutting and cheating on the math, but it's a legit cheat. It works. Okay. So I've got a net force of 58.86 newtons, and now I want to calculate the acceleration of the system, not just the tire. Okay, so I'm going to take my 58.86 and divide it by 38 kilograms, net force over mass. Right, and that should give me 1.5 meters per second squared, and now I can give a direction to the left. Are you all right with that one? Does anything change for question number 2? It's exactly the same as the example, except now it's saying calculate the acceleration for each object. So all I do is calculate the acceleration of the system and then apply directions that are appropriate for each part. The 8 kilogram mass downwards, the tire left, the 6 kilogram mass up, right? But other than that, it's exactly the same math I did before. Okay. Questions on that? Okay, reason we're going over all this system stuff, we're going to be doing a lab on Tuesday, and that lab is going to involve a pulley. We're going to hang various masses over a pulley and have them pull a cart. Okay, the mass of the system is going to stay the same. All we're going to do is take mass off the cart and hang it over the pulley so that we're constantly seeing the effect of changing the applied force on a system. Okay, but it's going to involve having to remember that it's the mass of the system and not just the hanging mass or not just the cart. Okay, another type of Newton's second law question. We call these static condition. What does static mean? Same, unchanged. Okay, here literally means not moving. So what does that mean for our net force? It's 0. In any static condition question, because there's no movement, the net force is 0. That actually makes these questions easier mathematically because you're being given the net force. As soon as it says the object's not moving, you know the net force is 0. You know all the forces in the question add up to 0. You know the acceleration is 0. So you're actually being given quite a bit of information when you're told that in this example the thing isn't moving. All right? So in this one here, we've got a store sign that has a mass of 35 kilograms and it's hanging from 2 different buildings. So there's going to be some vectors in here, right? So this is what I've got. All right, I've got 2 cables. One cable is attached to a wall like this, and it's angled 55 degrees below the horizontal. Okay, and the other cable is horizontal and is attached to a wall over there. That's probably the hardest part of the question, is to get the diagram drawn the right way. Okay, so this is cable 2. All right, so we gotta find the tension in cable 1. So there's 2 forces here, right? There's the force or tension of cable 1, and there's the force or tension of cable 2. Everybody okay with that? All right, what other force is acting in this system? Gravity. Okay, so the sign is 35 kilograms. And we know that gravity is acting downwards on it. Can I calculate that force? Yes. Okay, so 35, so we got 345.35? 343.35. Okay. That's all I can calculate right now. This is where this question becomes intuitive. Yeah, or has to be. It may not be intuitive, but it has to become intuitive. The sign isn't moving. So the force of gravity, the force in cable 1, and the force in cable 2 all add up to 0. Okay. Cable 2 pulls which direction? To the right. Okay? Cable 2 pulls this way, but the sign doesn't move. So that means there must be another force acting directly against it that is equal to it in magnitude. Would you agree? If the sign's not going to move, the only way the sign's not moving is if those 2 things are being offsetting each other. Something has to be pulling against cable 2 in the opposite direction. What is it? Cable 1. No. At this point, lots of people look at that and go, cable 1's pulling at an angle. How does cable 1 pull against cable 2? Well, anything that's angled has a horizontal component and a vertical component. Okay? Cable 1's got a lot of tension in it. It's offsetting gravity and cable 2. So it's got to pull pretty hard. Its horizontal component is equal to the tension in cable 2. Opposite in direction, but equal in magnitude. What's its vertical component equal to? Force of gravity. Remember, the sign's not moving vertically either. So the horizontal forces cancel, the vertical forces cancel. That's the part that's not about math. That's the part that's all about looking at this situation and being able to see the forces, right? And understand what's happening, right? Because so far, I've only done one calculation, and it was m times g. I mean, that's pretty simple, okay? I'm going to have to do one more calculation here, and I'll be done this problem, right? So I know this side here is 343.35 newtons. Can I find the tension in cable 1? Yeah, it's the hypotenuse of this triangle. I've got this angle, the opposite side to that angle, and I'm looking for the hypotenuse. Okay, what trig function do I use for that? Sine, yeah. All right, so I'm going to go the sine of 55 degrees equals the opposite side, which is 343.35, over the tension in cable 1. So I'm looking for the tension in cable 1. I'm just going to cross multiply here. Okay. Cable 1 equals 343.35 divided by the sine of 55 degrees. That's the only calculation other than calculating gravity that I have to do to solve this question. But a question like this really throws people because it doesn't seem to give very much information and asks you to calculate something that seems impossible at first glance. Okay, so cable 1 is pulling with 4.2 times 10 to the 2 newtons worth of force. Okay, 55 degrees below the horizontal. I would have to write that in there if that's the vector of that force. All right, that's tricky. Okay, like I'll give you that. That's a tricky question, not mathematically tricky. Right? But doing the sum, the vector sum of all forces in this one, yeah, I mean, we know it's 0, but figuring out what the forces are doing, that's the tricky part. Okay? Being able to look at something and go, oh, okay, what's going on here? Being able to visualize that, that's tough. Eventually, you're going to get to the point where you live in my world, where you see that stuff. That just becomes part of your world. It's not scary. Okay? Right? But when you look at stuff, you're seeing it from like a physics perspective, right? That's why like lots of action movies and stuff like that are just ruined for me, right? Because I look at them and go, that doesn't work in my world. Okay? In my world, I can't see how the forces would ever make that happen because it's not real. Okay? It's not believable. My suspension of disbelief is not there. That's the thing that makes movies work, is the suspension of disbelief, and it won't work for me. Okay? And sorry, but eventually that's going to happen for you too. Okay? You're going to be able to look at things and just go, oh yeah, well that's slowing down because of this, or that's moving this way because of that. Okay? And you just get better at it. It just takes experience. That's why we spend so much time on Newton's second law. Okay? It's not because you can't do the math. Obviously you can. It's not hard math either. Okay? But it's being able to gain the experience to see these different forces. Okay, questions on that one? See if you can figure that one out. It's not static. Okay, this is a Pulley question. Okay, so this 4 kilogram mass is sitting on this table. There's 32 newtons worth of friction acting on the 4 kilogram mass from the table. I want you to calculate the acceleration of the 5 kilogram mass. So, the forces acting in this system are friction, and gravity. Alright, so this is going to be 49.05 newtons. That's 32 newtons because that was given to us in the question. Okay? Are there any other forces? There are, but they don't matter. Okay? The two forces that are present but don't matter are the force of gravity acting on the 4 kilogram mass and the force of the table pushing up on the 4 kilogram mass. But because they're equal and opposite, they cancel each other out, so we don't have to worry about them. Okay, so now I've got the forces in here that I'm going to use to do vector sum of all forces. So my next step, calculate F net. So I'm going to have 49.05 minus 32, which is going to give me 17.05 newtons. Is that right? I shouldn't do math in my head, but I'm on a roll today. Okay. All right, 17.05 newtons is my net force. All right, they want the acceleration of the 5 kilogram mass. What do I do next? I divide, okay, m times a, but I divide by 9. See, I put one question in between the last time I told you. This is the most common mistake made on this kind of question. I put one question in between, okay, and people forgot right away. As soon as I say I want the 5 kilogram mass, we focus on 5 kilograms and we forget this is a system. All of the mass has to accelerate at the same time. So when I'm calculating the acceleration of the 5 kilogram mass, I'm calculating the acceleration of the system and then adding a direction onto it after. Everybody follow me there? Okay? So just wanted, I just totally did that to, mess with you and illustrate and make a point. Okay? All right. It's not that I'm trying to belittle you or make you feel small. That was an indirect result of what I did. Okay? Yeah. All right. 17.05 newtons divided by the mass of the system, 9 kilograms. All right, that's going to give us 1.9 meters per second squared. Okay, that's the acceleration of the system. It wanted the 5 kilogram mass. Down. Okay, question?
Would it be one significant digit?
It would. So, you're right. Okay. Any other questions on that one? All right, I think my next one is, no. Try this. Those two cables are identical. Calculate the tension in either one of them. You may. And by the way, this is just hanging there. It is not moving. Okay, so it's another static question. Jeff, you had a question? Just in walking around, I saw people doing a good job of this, but a lot of people making the same mistake, and it's the one I wanted to point out with this example, actually. Okay, so what I saw most people doing is recognizing that, yep, each one of these cables has a triangle that looks like this, all right? And the angle inside of that triangle is 50 degrees, half of the 100, right? That's good, that's the first step, right? They also recognize that there's a force of gravity pulling down on this 50 kilogram mass of 490.5 newtons, which is also, here's where people messed up. How much of this force is each cable holding? Half. I know, it's so frustrating, right? You're like, oh, I had it all, and then you went and said this side was 490.5 and used it for this triangle. Well, if that's the case, then the net force is not 0. The net force is 490.5 newtons because you got 2 cables pulling that hard, okay? And this thing is flying up in the air, okay? Really fast, all right? And I'm not saying that again to make fun of you guys. I knew people would make that mistake, and I'm just trying to point out the places where people can go wrong, okay? And see, all right, these are the things I have to consider. So this side is actually only 245.25. Yeah, newtons. Okay, if I'm talking about each cable, right? Each cable is holding half of the weight of this thing here. All right, so now I've got 245.25 on this side. I've got this angle. I'm looking for this. It's the adjacent side. So I'm going to go tension equals 245.45 or 0.25, sorry, the adjacent side divided by the cos of 50. Okay, and that will get me the tension in that cable. So I like that people were getting the hang of this and they had it drawn correctly. I kind of figured that, like I say, that one thing would probably happen. Okay, so we're looking at a tension of 3.81 times, or we could say 382 newtons. I think we have we have 3 significant figures here. No, we only have 2, 50 kilograms on the mass. So 3.8 times 10 to the 2 newtons. Okay, and that would also have to have a vector at 50 degrees from vertical. Or 40 degrees from horizontal, whichever. All right, so feel good about what you did there, okay? You should. That's a big step, being able to visualize those forces, okay? But understand, there's always one more trick. Okay? Always one more trick. Got to be ready for those little things. Okay. We did one like this yesterday. System question. Right? I want you to see how much you remember from yesterday. So the total friction on the whole system is 120 newtons. The friction on the 40 kilogram mass is 48 newtons. Okay? I want you to calculate the acceleration of the 40 kilogram block, this one, and calculate the tension in cable B. This is exactly the same as the question we did yesterday. Okay? I just want to see how much you remember about how this works. So the whole system is being pulled this way by this force, 150 newtons, and that's directly attached to the 40 kilogram mass. Give you guys a little bit of time on that one. All right. Is the acceleration of the 40 kilogram block the same as the acceleration of the system? Okay, so that's what I want to calculate first. That's the easiest thing to do as my first step, is just to write this as a 100 kilogram mass being pulled this way by 150 newtons. Okay, and resisted by 120 newtons. Okay, that means my net force is 30 newtons forwards, and I can calculate the acceleration by just going 30 over 100, which will be 0.30 meters per second squared forward. Okay, so the first part, pretty straightforward, just a standard Newton's second law kind of question. Now, find the acceleration of the 40 kilogram block. Done that. Calculate the tension in rope B. How many ways are there for me to do this? 2. Back box or front box. Doesn't matter which one I use, I will get the tension in cable B. Right? I'm going to use the front box just because I want to. Right? So 40 kilograms, it's being pulled this way by 150 newtons. It's being resisted by 48 newtons worth of friction. Question told me that. And what else is resisting it? The 60 kilogram block, which is going to be the tension in B. Okay, that's the other force pulling backwards on the front block, and that's the one I'm being asked to find. All right, can I find the net force acting on the 40 kilogram block? Using mass times acceleration. Okay, so that'll be 40 times 0.3 Alright, so 12 newtons is my net force. 12 newtons forward. Okay, and the other way to calculate F net is the vector sum of all forces. So that'll be 150, okay, the force forward, plus 48 newtons, but negative because it's backwards, plus negative tension in B. Okay, which is the thing I'm being asked to find. Alright, and I'm not even going to put the negative on there, it's just going to come out that way when I calculate it. So to calculate the tension in B, I'm going to take F net, I'm going to subtract the 150, I'm going to subtract the negative 48, and that will get me my, sorry, that F net has a number, I already calculated it, 12. Okay, 12 minus 150 minus negative 48, so okay, so we got negative 90 newtons being the tension in the cable between, or the rope between the boxes. Everybody okay with that? 11:18. Okay, you know what? I think we're going to call it, oh, look at that. Oh no, we did that one already. On Monday, we're going to start talking about inclined planes. Yay. What's that? Yay, yeah.
Pass
Okay.
on offer.
You will, yeah. It's important to learn how to do these or you will become an inclined plane wrapped around an axis. You will be screwed. An inclined plane wrapped around an axis is a screw. And if you don't learn how to do it, you will be one. Screwed. Yeah. Okay.